In my earlier video, I had discussed about properties of rank and some example which had come in different type of competitive exam based on this property. Today I will discuss some question also. First question had come December 2014 exam. The question is, consider AB n cross n matrix such that BA plus B square equal to I minus BA whole square, where I is the n cross n identity matrix. Then which of the following always true? Option 1 A is non-singular, option 2 B is non-singular, option 3 A plus B is non-singular, and option 4 AB is non-singular. The question about non-singularity of A, B, A plus B and AB. From this equation, since here BA plus B square equal to I minus BA whole square, that implies BA plus B square plus BA whole square equal to identity, and from this equation this implies obviously B times A plus B plus A square equal to identity, and this equation imply either B equal to identity and A plus B plus A square equal to identity. And since always B equal to identity, from this equation this imply, then obviously option 2 always true. And from this equation A plus B plus A square equal to identity, now put the value of B, that would be A plus identity plus A square equal to identity. That imply A plus A square equal to 0. Just common A, then this would be I plus A equal to identity. Therefore, this imply either A equal to 0 or A equal to minus I. Okay? Are you getting the equation? Since here two cases arise for A, that means obviously either A equal to 0 or A equal to minus I. That means that imply either A is singular if A equal to 0 or A is non-singular. Okay? That means we cannot tell exactly A is non-singular. A can be singular or A can be non-singular. That means option 1 is a wrong option. Okay? Question about A plus B and AB. Here A plus B, just put the value, B always identity, but A can be either 0 or minus I. Okay? That imply when A equal to 0, that imply this sum is identity, but when A equal to minus I, then minus I plus identity equal to 0. Okay? That means A plus B can be either identity or 0. That means that imply A plus B is either singular or non-singular. Okay? Similarly, AB. B is always identity, this is true, but when A equal to 0, then AB equal to 0, and when A equal to minus identity, then AB equal to minus identity times value of B always identity. That means this would be minus identity. Means similar to A plus B, either A plus AB is 0 or AB is minus identity. That means we cannot actually tell about A plus B and AB. Okay? That means option 3 and option 4 is a wrong. Now I will say one question which had come December 2014 exam. The question is, AB 4 cross 7 matrix and BB 7 cross 4 matrix such that AB equal to identity matrix. But AB equal to I4, that means ABB 4 cross 4 matrix. Where I4 is the 4 cross 4 identity matrix, then which of the following is an R-true? 1. Rank of A equal to 4. Option 2. Rank of B equal to 7. Option 3. Nullity of B equal to 0. And option 4. BA equal to I7, where I7 is 7 cross 7 matrix. This is very interesting and very important question. This type of question I had discussed in my previous video. At first, think oneself. First, pause the video and try to oneself to solve this problem. Then, restart my video also and check the solution. Then idea will be more improved. Solution is such type and AB equal to I4, where A is 4 cross 7 matrix and BB 7 cross 4 matrix such that AB equal to I4. We all of us know this theorem. If C is M cross N matrix, then rank of C always less than equal to minimum of M comma N. Therefore, since AB 4 cross 7 matrix, so rank of A always would be less than equal to 4, and B is 7 cross 4 matrix, so rank of B less than equal to 4. By this theorem, rank of AB less than equal to minimum of rank of A comma rank of B, then rank of AB less than equal to rank of A and rank of AB less than equal to rank of B. And since AB equal to I4, therefore we can write 4 less than equal to rank of A and 4 less than equal to rank of B. Okay, and I have got rank of A less than equal to 4 and rank of B less than equal to 4. Therefore, this is also less than equal to 4 and this is also less than equal to 4. So, by this expression, we can tell rank of A equal to 4 and rank of B equal to 4. So, option 1 is a right option, but option 2 is a wrong option because I have got rank of B equal to 4. Here the question about nullity of B. That means I will apply here the rank nullity theorem. By rank nullity theorem, we can tell rank of B plus nullity of B equal to dimension of B. Since rank of B equal to 4, that means put the value here nullity of B, and dimension of B, V means since BB 7 cross 4 matrix, that means there exists a linear transformation from R4 to R7. So here dimension of the vector space is 4. That imply nullity of B equal to 0. Okay. Option 3 is a right option. Option 4 indicate BA equal to I7 where I7 is 7 cross 7 identity matrix. This is rank of BA obviously less than equal to minimum of rank of A comma rank of B. That means similar to AB, rank of BA also less than equal to rank of A and rank of B. And rank of A also less than equal to 4 and rank of B also less than equal to 4. So, BA equal to I7, this is cannot possible. So, option 4 is a wrong option. Are you getting why this theorem is very important? I have told you in many times. If you know this theorem, then you will solve this question very easily. Otherwise, this is not possible. Okay? Now I will see one question which had come December 2016 exam. The question is such type: A equal to Aij, B and n cross n matrix such that Aij is an integer for all I and j. Here notice is entries of A be the integer entries, and consider AB equal to identity with B equal to Bij, where I be the identity matrix. Then for a square matrix C, det C denote the determinant. Then which of the following statement is true? Option 1, if determinant of A equal to 1, then determinant of B equal to 1. Option 2, a sufficient condition for each Bij to be an integer is that determinant of A is an integer. Option 3, B is always an integer. And option 4, a necessary condition for each Bij to be an integer is determinant belongs to the set -1 plus 1. Okay? Given AB equal to I. And in for option 1, the condition is if determinant of A equal to 1, that imply determinant of B equal to 1. Given determinant of A equal to 1, that means obviously A is invertible. And given AB equal to I, since determinant of A equal to 1 means A is invertible, now multiply this equation by A inverse. Then this line imply B equal to A inverse. Now apply det both sides, then this would be determinant of B equal to determinant of A inverse. And since here given determinant of A equal to 1, that means obviously determinant of A inverse and determinant of A is same. This is equal to 1. Therefore, option 1 is a right option. If determinant of A equal to 1, then that implies determinant of B equal to 1. Option 2, a sufficient condition for each Bij to be integer is that determinant of A is integer. Is it true option? We all of us know. Notice actually B equal to A inverse, and we all of us know the formula of A inverse is actually adjoint A by determinant of A. For this, consider one example. Consider this matrix, and notice here determinant is -4, which is actually not equal to 0. That means which is obviously belongs to integer. But notice the B matrix. This is actually the inverse of A. This matrix not belongs to integer. Okay? Here the entries of B not belongs to integer. So this is not sufficient condition for each Bij to integer is determinant of A is integer. This is not sufficient condition. So option 2 is a wrong option. And option 3 also wrong option. B is always imply integer. Option 4 is very interesting and very important option. Option 4 indicate a necessary condition for each Bij to be integer is determinant of A belongs to the set contain -1 1. Notice here B equal to actually A inverse, and all Bij be integer. This is possible when determinant of A belongs to -1 1. This is just actually the nice theorem. This is actually the idea about the unit of integer entries of group theory. We all of us know for integer the units are always -1 and 1. So there exists a nice result. If A be an n cross n matrix over integer, then A inverse always has an integer entries if determinant of A plus minus 1. So this option is always true. The condition for each Bij to be an integer and entries when determinant of A belongs to minus 1 1. Now I will see one question which had come December 2011 exam, and this question is part C question. The question is, consider a matrix A which entries are Aij n cross n matrix with integer entries such that Aij equal to 0 for I greater than j and Aii equal to 1 for I equal to 1 to up to n. Then which of the following properties must be true? Notice this consideration here very important. Aij equal to 0 for I greater than j and Aii equal to 1 for I equal to 1 to up to n. Then which of the following properties must be true? Option 1, A inverse exists and it has integer entries. Option 2, A inverse exists and it has some entries that is not integer. Option 3, A inverse is a polynomial function of A with a integer coefficient. Option 4, A inverse is not a power of A unless A is an identity matrix. Here the question about n cross n. Now consider n equal to 3, then consider this arbitrary matrix. Since the condition Aij equal to 0 for I greater than j and Aii equal to 1 for I equal to 1 to up to n, then the matrix would be such type Aii equal to 1 and Aij equal to 0 for I greater than j, then this would be A12, A13, A23 and this part would be 0. This is our considerable matrix since Aij equal to 0 and Aii equal to 1. That means this is actually the upper triangular matrix with eigenvalue 1. Okay. Notice here the question about A inverse. Obviously A inverse means adjoint of A over det of A. And what is the det of A? Since all eigenvalue here 1, that means obviously det of A equal to actually product of eigenvalue which is equal to 1. That means A inverse equal to just adjoint of A. First option noticed, this is indicate A inverse exists and it has integer entries. And notice here the considerable matrix B, integer entries. So remember this result which I have told you few minutes ago. The result is if A is n cross n matrix over integer, then A inverse also has an integer entries if determinant of A equal to plus minus 1. I had discussed this result few minutes ago my previous example. And notice since here determinant is plus 1, so obviously this A inverse would be belongs to integer. Now notice the first option. First option indicate A inverse exists and it has integer entries. Obviously this option is true. And second option indicate A inverse exists and it has some entries that are not integers. This is wrong option. Now notice option 3. Option 3 indicate A inverse is a polynomial function of A with integer coefficient. Since here the eigenvalue is 1 1 1, so since here the eigenvalue are 1 1 1, that means the characteristic equation of A is lambda minus 1 times lambda minus 1 times lambda minus 1, which is actually equal to lambda cube minus 3 lambda square plus 3 lambda minus 1 equal to 0. And by Cayley-Hamilton theorem, since every matrix satisfies the characteristic polynomial, then this would be a cube minus 3a square plus 3a minus identity equal to 0. Now multiply this equation by a inverse on both sides. Then this would be a square minus 3a plus 3i equal to a inverse. And from this expression we can tell, obviously a inverse is a polynomial function of a with integer coefficient. Okay? OL. So, option 3 is a right option. A inverse is a polynomial function of a with integer coefficient. Okay? And option 4 indicate a inverse is not part of a unless a is an identity matrix. For this, has considered a inverse is not part of a unless a is an identity matrix. So, for this proof, consider a inverse is a part of a. So that imply a inverse equal to a to the power m, where m belongs to natural number. That imply I equal to a to the power m plus 1. That means here a satisfies actually this polynomial x to the power m plus 1 minus 1 equal to 0, and this is actually the annihilating polynomial. I hope my all viewers have understood this. And minimal polynomial always divide the annihilating polynomial. So minimal polynomial obviously divide x to the power m plus 1 minus 1. So by this expression we can tell minimal polynomial divide x minus 1 times x to the power m plus x to the power m minus 1. Up to this would be continue plus x plus 1. And since a has only one as a eigenvalue, so only possible minimal polynomial would be x minus 1. That imply actually this would be a minus identity equal to 0. So a equal to identity. Okay? That means a inverse is a part of a. That imply a is actually identity matrix. Since option 4 is the right option, a inverse is not part of a unless a is the identity matrix. So, are you getting the question? This question is actually conceptual question. Very important. Okay? OL. Today, I will stop here. In my next video, I will discuss this type of question, different type of question. Actually, linear algebra is very important for any competitive exam. So, at first I will highly recommend you in my today's video with pay attention. And if you don't see my previous video, at first see this previous video because this is very important for any competitive exam. See you soon. Stay safe and stay positive always. And don't forget to subscribe my channel for more videos. Thank you so much.